Hello. Yeah, so today I'm going to talk about why tech is weird. So I'm Harsh Gupta. I'm an undergrad student at IIT Kharagpur, a fifth year undergrad student. And here are my contact details. This summer, I interned with Center for Internet and Society, working on encrypted media extensions. So encrypted media extensions is a draft proposal by W3C, World Wide Web Consortium, to facilitate digital rights management in video. So EME slightly helps content providers with piracy, but it opens up big issues about interoperability, security, accessibility, and privacy. And the proposal has been really controversial. If you go up to EFF website or FSF, you'll see there have been huge protests about that. So I analyzed who participated in the debate. So there were 472 emails sent on the public HTML mailing list of W3C with EME, encrypted media, or digital rights management in the subject line. And there were 48 people who sent those many emails. 310 emails were sent by 13 North Americans, 146 by 13 Europeans, 16 emails by 5 people from Australia or New Zealand. And there was absolutely no one from Asia, Africa, or South America. Absolutely no one. And this is weird. Weird is the Western educated, industrialized, rich, and democratic people who are participating were weird. And and that's almost 12% of the world, but W3C and we in general are making tech for the world. So in this specific case, lack of weirdness is important because IP, intellectual property laws vary across the countries, but in this debate there was all the debate was around the US laws. Cultural attitudes differs. The media industry, how they work and things differ, and so tech is being designed for you people, for weird people, but thinking of weird people, but it will affect everyone, including us, including people in India, South America, South Africa. And more generally, this is important because because the world is being decided for everyone else, when we don't get to have a seat, we don't decide the future for ourselves. So make tech less weird. Thank you.
Thank you, Harsh. I think normal is also an acronym. All right, next up is Brian McPhee. Next up on deck here. And right now we have JetBrains. So, Brian, are you around?
Yep, right here. What? How do I connect this?
Right there.
Oh, okay. Okay, hello. So my name is Brian, and I'm a software engineer at JetBrains. And today, for my lightning talk, I'd like to introduce a tool that we're working on in order to improve the workflow of data scientists. Particularly, the premise of our product called Datalore is that it is an intelligent notebook that is infused with editor-like functionality, and that we're trying to make this tool follow your workflow from end to end, beginning with your data munging, your data processing, up to your model building, and once you're ready to build your models and scale up, even follow you to cluster deployment, and later, finally, analysis of your code, and where you want to display your outputs to your end users. So our main features are listed here, and so we're going to move over very quickly to our live demo. So the first thing you'll notice about our tool when you play around with it is that it's a fully interactive editor. As soon as you edit code, it'll automatically recompute in the same way that a spreadsheet might recompute. Meaning that as soon as I edit code in this cell, it'll also track your dependencies between cells below in order to figure out which ones may have changed and recompute them accordingly. This is, I want to note, a very easy setup. This is easy to reproduce, and we have a library manager that will automatically set your version of different libraries, right as you can see here. So as you can see, you can set the version, and if there's a library that you do not have, you can easily install it using one click and specify a version. So this editor is also very interactive. So, collaborative, meaning that multiple people can edit it. So I'm going to open a new workbook, and many people are going to be able to work on it all at once. So I have my teammates here. They're typing along with me, and I am working together with them in an almost pair programming style. So this product also has, as the previous talk mentioned, integration with version control. Version control is one of the most painful parts of working with a notebook, so we've integrated it into our internal tool where we track the differences between different workbooks, and as you can see, they're highlighted in different colors. So this tool, as I earlier mentioned, also has much more code-like functionality, or like an editor-like functionality, where you can move to code declarations. It has error highlighting. For instance, if I remove the parentheses on this plot on this line, it becomes red. It has auto-completion. For instance, plt dot annotation, for instance, and it can also do code analysis. If I remove this code here, it'll sense that you're missing some imports, and it'll suggest to you maybe you want these fancy libraries in your code. So this is still in private beta, and we encourage you people, or we would really appreciate feedback if you send by signing up at our website, jetbrains.com/Datalore, or if you can visit us in our booth. And so thank you very much.
Thank you, JetBrains. Certainly seems like a next generation tool. All right, so Brian is up next, and then after him will be Nora.
Do you have HDMI?
Are you here, Nora? Oh, okay. We do have HDMI.
Oh, well, too late. It's always too late. No, that's not me, that's my dog. Okay, we'll do it this way. Already? No. No, I'm not done yet. Okay, I'll do it this way. There we go. Okay, so this is a project that ate up a couple of weeks of my life because things are painful. Hopefully someone here can use it. I work in audio, and I often have to change the sampling rate of signals. This isn't just for that, it's also for things like wavelet pyramid decompositions. You end up doing this a lot. So SciPy does this for us. SciPy, open up the signal submodule called resample. What it's going to do is take your waveform, do an FFT, truncate or expand it, and then invert that FFT. Those bits in red there at the top and bottom, those are really slow. Really slow. If you think about X being maybe 100,000 samples, you have to touch each of those samples before you can do anything. Okay? So you can't do anything on long signals. Okay, so that's not a great option. We also have libsamplerate and scikits.samplerate. These have been around for a long time. They're very good. But they're kind of a pain from a packaging perspective. They're kind of really a pain. If you have these as a dependency, it makes it very hard to satisfy user constraints if they're not experts in building stuff. So that's no good. Also, they haven't been updated in a long, long time. I'm not sure if it's abandoned or just cool, it works. So anyway, I eventually got frustrated with all of that and rewrote it from scratch from the original paper. And that's what resampy is. It's rewritten in Python, has a BSD-style license. You can do whatever you want. It's easy to modify. It exposes all the parameters, window functions, anything you want to do with it, anything you want to know about, what's the roll-off of this filter, it'll tell you. And I haven't abandoned it yet. Give it like another couple of weeks. And just to drive the point home, here's kind of a runtime comparison of resampling about 18 seconds of audio at 22 kilohertz to 16 kilohertz. Resampy takes about 300 milliseconds. SciPy signal takes about 7 minutes. So if you have like 3 minutes of audio, good luck. That's it. Thanks.
Thank you very much, Brian. All right, so next up is Nora, and after her will be Stefan. You around? Yep. Thanks.
There we go. Okay, hi, my name is Nora DRAM. I'm a developer at Enthought, and I wanted to talk about a project that I've been working on recently that I think is kind of fun. So this spring, an international team of scientists went out into the Gulf of Mexico to drill into the Chicxulub crater. This is thought to be the impact crater left by the asteroid that killed the dinosaurs 66 million years ago. And one of the interesting things about it is that it has the only intact and accessible peak ring structure in a crater on Earth. That's the inner ring that you can see on the image. We observed those on other planets as well, and so we'd like to know how those actually form, how the rocks are moved around on impact to get there. So this team went out into the Gulf. They have a ship. It jacks itself up on 3 pylons and goes down, and they drilled out 835 meters of core. And this is also fun because this is about 10 times longer than any of our core projects that we've worked on so far, so data is fun. And where we come in is with our virtual core product. Some of you may have seen Brendan Hall's presentation yesterday that was talking about how we're using scientific Python in there. If you haven't, I recommend you check it out. But essentially, this application is used because they will take these rock cores, these 835 meters of actual rock, and put it through a medical CT scanner, get a few 100,000 files out of that. We take all of those, we clean them up into a 3D volume, do some additional processing. You can see some of the libraries that we're using as we're doing that to both clean up the data and then detect bedding, do some texture analysis, and so on. So I wanted to quickly bring up, this is that actual core. This is about the first 15 meters. You can see this, it's a fully Python application. And so what we'll be able to do is make available this both in our desktop and web viewer for the scientists to actually look at what's going on inside the core. And so just wanted to pull out a little bit of this. You can see in the bottom right kind of this interesting texture of rock. There's some marbling going on there. And I've just pulled that section up in our volume viewer, where you've got these widgets that you can go in and kind of pull out these different densities of rock to see how everything is put together. And that's also useful for if you're trying to pull out how the rock fractured, for example, after a big asteroid hit it. So If you're interested in hearing any more about that, you can check out our virtual core webpage, check out Brendan's talk, and for the volume viewer, that's all built off of MyObby, and then those widgets are through the Ensemble package. So, thanks.
Thank you, Nora. I totally dig it. All right. Next up, Stefan, and then after Stefan will be Megan Ling. Oh, okay, great. Thanks.
Is this the mic? I need my cliff notes here. Okay, you ready? Yeah. Hi, everyone. It's good to see all of you here again. This is a weird thing to say, but I'm sorry I didn't prepare a lightning talk. Like I felt like previous years we spent very little time preparing them, and now they're like super polished presentations. But I'm just here to tell you something that I think is cool. And Brett will be demoing for me. So you saw this. Some of you saw the CCM talk early on today. For the CCM talk, we have a bunch of processes that we fire off from the front end. Oh, you can't hear? Okay. Is that better? Oh, it's there. All right. Better? Okay. So for the CCM project that you saw earlier on, we often have long-running tasks. So you click on a button on the website, and then the backend goes off, and it does some long-running machine learning task. So traditionally what you would do is you would send off that task, and then you would go back every 10 seconds and say like, are you done? Are you done? Are you done? Are you done? And that's annoying to the backend. It's annoying to the programmers. It's just annoying overall. So what you really want is just to have a WebSocket that sits between the backend and the front end and is able to send the result back as soon as you're done with it. So that should be really easy to do. And it turns out in Python, it's not nearly as easy as it should be. So what we did as part of the CCM project is we developed a little demo application. We call it Message Flow, and it allows you to very easily hook in this kind of WebSocket infrastructure into your own project. So there's a little project you can clone on GitHub, and it gives you all this functionality for free. It's about like 100 lines of code. It's not complicated at all. Brett will demo to you what this thing can do. So this is just showing that if you're in an IPython terminal, you can send a message through to your web browser front end, and the web browser can receive that message and do something with it. So there's the pop-up that just displayed. That was an information message. You can change it a little bit, send through an error message. You could send a bunch of them through if you want to. So there's a whole bunch of them. If you add a new object into the database on the Python side,
Matthias was distracting me, I'm sorry.
it's fine. Matthias always does that. All right. So if we add a new object into the database, we can ask the website to refresh itself. And boom, and the new results appear. So if you want to know how to do this in your own project, you can go to the CCM website. It's ccm.ml. Can you show that, Brett? And if you click on the blog in the top, there's a whole article I wrote up, a pattern for WebSockets in Python, that shows you exactly how to do this. The architecture is fairly uninvolved. There's a Flask web server. You could use any web server you want. You don't need to use Flask. You can use Tornado or Django or whatever you've got. Django has now got their own channel system, but I don't know what they're doing there. And then you have another little server that just handles the WebSockets, and a very simple way of authenticating between those two. And you run Nginx as a layer on top that distinguishes between the requests that come in either for the WebSockets or the web server. And that's it. So it's about 100 lines of code. And yeah, read the blog and feel free to ask me any questions you may have. Thanks.
Thank you, Stefan. And Megan's up now, and after her will be Todd Tomaszek. You around? Oh, there. Perfect. Great. Thanks. Take it away, Megan.
Okay, so I wanted to talk to you about a project I've been working on using Voronoi tessellation from a C++ package wrapped in Python for astrophysical dataset analysis. So a common problem in astrophysical simulations, when we run these simulations of dark matter structure formation, we want to say something about that structure. But typically the parameters we use to describe the structure assumes that it's very ideal. It's spherical, smooth, very simple, but in reality it's very complicated. So naturally, as you'd expect, this leads to bias in the results that you get, and so this is not something we want. We can get around this by using a technique Voronoi tessellation, where you divide up the domain between points in a simulation, such that you can actually get a volume and density for each point. Now, to do this on the data sets, there are existing codes in C++ that do this, and that's great. So I ran with that. I wrote code to load in my data set in C++, write it out in a format that I could then load in Python and actually do my analysis. But then I ran into the issue of, what if I want to load a different type of data? What if I want to use additional Python tools on the actual tessellation? What if the data set is too big and it takes a really long time to run? So then I turned to Python, because everyone has tools for loading their favorite type of data in Python. They already exist. You don't want to have to rewrite them in C. In particular, I use the YT interface for loading the astrophysical data sets, because it supports a wide variety, and there are a lot out there. And so this gets the data into Python. But then we have the problem that Seagal's in C++. So we take Python, wrap it around there, and now we're happy. We can get our data in, we can get the tessellation, everything's good. But what happens when the data gets big? We're not so happy anymore, because it takes a really long time and sometimes it won't even fit in memory. So what do we do then? So in that case, then we can actually break the data up using some sort of domain decomposition, such that we can process and do the tessellation on each subset of the data separately, and then everything's good again. So here is an example of a tessellation in 2 dimensions using a KD tree to break it up. And so the current state of the code is that I have wrapped the Seagal functions for computing the tessellations and directly exposed the Voronoi volumes to Python and output all the necessary neighbor information. It's parallelized using MPI for pi, and the domain decomposition is done using a KD tree. Periodic domains are supported, and it takes about 20 seconds for 1 million points in 3 dimensions on 10 processors. So you can run this on a very small machine. Things that I still need to do, expose the neighbor info directly to Python so that you can actually get information about the graph, the connections between the particles. Add additional domain decomposition options. And also, what I really am working on right now is incremental processing for large data sets where you can't have it all in memory at once. For instance, it would take like 30 gigabytes to do a tessellation over 1 billion points in 3 dimensions, which is not great. So if you are interested in this package, please contact me. It's very preliminary. There's not even a page for it yet, so email me.
Thank you, Megan. No one touched that tile. All right. Todd is up now, and after Todd, Rowan Cockett. Are you around? Rowan? Yeah. Over there. Okay, great.
Hi, my name is Todd, and I work for Intel, and I'm just here to briefly tell you about the Intel distribution for Python. First of all, our goal is really just to deliver the best possible performance on Intel architecture for you and for Python developers and users. At the end of the day, ultimately what we really want is just for your stuff to run as fast as possible on our stuff. And the way that we do that is by building and linking CPython and Python packages against some of Intel's high-performance low-level libraries. Those being the math kernel library, our data analytics acceleration library, our integrated performance primitives library, and threading building blocks, or TBB. A couple things that we are not. Number one is there's no license fees or anything for the Intel distribution for Python or any of our packages. It's free, it's redistributable, it's publicly available. And the other thing that we're really careful about is that we really did not want to be just another competing Python version out there in the marketplace. Nobody wants that. We didn't want that. And so we're really striving hard to be cooperative and to be complementary of what is already out there in the marketplace. We've been working pretty extensively with Continuum Analytics. Our distribution of Python uses Conda as its underlying installation and package management. So you can add the Intel channel on anaconda.org. You can get our beta packages right now by adding that channel and simply Conda installing them. And we also have a standalone installer that includes all the packages, to basically the SciPy stack and a few other performance packages that we provide. And Intel is making much more of an effort to be active in the community. So we're sponsors of several conferences. And what we're trying to do with any changes that we happen to make in source code to enable optimizations is we're trying to upstream those to the public domain as much as possible. This just gives you a little example. At the 100% line, that's native MKL. That's kind of ideal native performance. The gray lines will show you that the Intel distribution has a very thin layer of enabling of Python there. So we get near 100% performance based upon native MKL. And then the others are non-accelerated or open blast implementations. If you were here to hear my colleague Anton Malakov's talk on threading building blocks, we have an implementation in Python library that allows for composable multi-threading. It avoids oversubscription. And this is a simple example that shows you can have nested parallelism that as you add additional parallelism, you actually lose performance. But that final column is with TBB enabled with MKL and outside parallelism, and you can unlock more performance because you don't have as much contention. We also have our data analytics library. I can't get into a whole lot of details on it, but it's also included in our distribution. It works with MPI for Pi and PySpark. And here, just a sample of some of the performance benefits that you can get by using PyDal. Another thing that's not part of the Intel distribution for Python, but something that Intel is working on our ecosystem is mixed mode profiling. So our vTune profiling application now supports Python, so you can do not only Python profiling, but mixed mode profiling for your applications. And right now we are in beta, and you can, like I said, you can get either go to Intel's website and download the distribution. You can get it through anaconda.org. We expect within the next few months to be fully released, and we certainly welcome all of your experiences with the product. Thank you.
Thank you very much. Up now is Rowan, and then following Rowan is Matar. Are you around? Yep, okay.
So I'm Rowan. I work at 3 Point Science. And one of the things that I'm doing here is working and talking about a package that we're developing for simulation and parameter estimation in geophysics. And that really means that what we want to do as geophysicists is have all of the simulation tools in one place, and so that we can sort of mix and match them. So that's electromagnetic data and seismic data and things like that. But another thing, and this is sort of where I have my 3-point hat on, is we want to communicate those results to other people. And so the geologists don't use the same sort of tools as us, and the hydrogeologists don't use those tools. So the communication and collaboration across these disciplines is actually quite difficult, and it's been something that we've been looking at for a while at 3-point, and especially in the 3-dimensional space. So the Earth is in 3D. So we need to communicate in 3D. And so the sort of typical workflow that we're going through right now is we collect the data, the geophysical data, and then we analyze it, we optimize, we do an inversion, and we create some 3-dimensional pictures of the Earth. These are our models, and we create surfaces from those that we need to communicate with the geologists. And so how we communicate those things is statically. So we use PowerPoints, we use PDFs, and this means that you're showing people you want to have a conversation to make a decision, but that pipeline of communicating with them is so compressed. Those tools are not allowing us to do our best work and make our best decisions. And so these are the types of problems that we've been thinking about at 3-point. And we've been creating some tools that sort of have allowed people to play around. So having a geologist, a geochemist, and a geophysicist all in the same room and sort of interacting in a web-based environment around these 3-dimensional models. And so a lot of those tools were sort of one-offs, and what we've been learning and I'm presenting on today is Steno 3D. And so Steno is a shout out to Nicholas Steno, who's one of the fathers of geology, and then stenography, which is the act of taking notes in a meeting. And so it's that collaboration around your 3D data that we're trying to support. And so there's a dashboard in Steno 3D, so go to steno3d.com and you can sort of upload some data, and you get into this environment and you have a dashboard, and you can click on one of these and you get your sort of 3D environment. And so this is all web-based, and so it works really well on multi-touch and having a tablet, and you can toggle things on and off. You have some slicing capability, you have some select capability, you can scrub through your data, things like that. But one of the things, again, that we want to support here is the collaboration around these data sets. So capturing the same way that we would in a PowerPoint slide, those 3-dimensional slides. And so down here, we actually have a talk sort of prepared that actually Brendan made. And so he has gone through and he's made some annotations. And so he's talked about this unit. Is this a kimberlite pipe? I don't know. So we can walk through the sort of the story that he has prepared for me. And I can ask him some questions and ask him, like, what is this? Maybe sort of circle it. And just save that annotation. And then if he's on that dynamically, it's updating because we're on the web. And playing around with slicing again, you can get more details about the data and things like that. And we've been working a lot with other technologies, and I'm out of time. So it works in Python. It has a Python API. So you can download it, install it. You should look at the documentation and go to steno3d.com. Thank you very much.
Thank you. All right, up now we have Matar, and then following her will be Nathaniel. Yep, all right, perfect, great.
Okay, Hi, I'm Matar, like guitar, and I'm here to tell you about Insight, which is Insight Data Science. It's a free fellowship for people with PhDs that are in academia and thinking of transitioning to industry. So I'm currently an Insight Fellow, and as fellows, we work on either consulting projects or independent projects, and I'm just here to show you my 3-week consulting project. So I worked on a project for a startup called DeepGram on automatic speaker segmentation. So companies have a lot of very valuable but often neglected audio data. So anytime you call a call center and you hear this call may be monitored or recorded, the companies are collecting this data, but the truth is it's really difficult for them to extract value from this data. So that's where DeepGram comes around. They essentially developed a product that makes, it indexes audio and makes it searchable. So for example, you are a company and you're searching through your audio stream, and you notice that slowly but surely, the number of times that your competitor is being mentioned in your call center is increasing. This is a business problem. But it's important to know who is mentioning your competitor. For example, is it your customers that are calling in and saying, oh, I would really prefer to go to your competitor? Or is it your customer service representatives that are maybe recommending your competitor? So that's the problem that DeepGram came to me with. They said, okay, we can index audio, but what do we do if there are multiple speakers? So for my 3-week consulting project, I basically came to them with the deliverable, which was production-ready code, where inputting just a recorded conversation, you would output who is speaking at what time in an unsupervised manner. So what does that look like? What you're going to hear right now is just an audio stream of 2 people, and at the bottom, you'll see who the algorithm identified as speaking.
But we're lucky in the Bay Area. My loyalties to the Sharks and the Warriors, the Giants, Niners have been pretty good now, maybe not so good, but we've had some very good teams in the Bay Area.
I've also been caddying
it'll
a
also
lot.
track
I'm going to be
when they're
caddying,
interrupting each
on
other,
Monday
when
for
they're
my oldest son
laughing.
as he tries to make the U.S. Open for a second time.
That's exciting. I know you're a very serious
Really
golfer.
fascinating, exciting, yeah. So how is this done? So basically, given just an audio file, I calculate sliding windows of 500 milliseconds each. For each window, I calculate, I take the spectral decomposition and I calculate MFCC coefficients, which are Mel frequency Kepstrom coefficients. These are essentially just spectral coefficients that map really well to how we perceive speakers. And these coefficients are used a lot in speaker recognition algorithms. So after calculating these for every sliding window, I end up with a matrix, which basically for each timestamp, I have my coefficient weightings for the MFCCs. And what I want to do is essentially blindly segregate this matrix into an assignment for each of the timestamps. So the first thing I want to do is I want to project this matrix into lower dimensional space and see if there's some sort of structure in that lower dimensional space. For that, I just use PCA, and you can see that 60% of the variance is accounted for by just 3 principal components. So that's nice. So I can take that data and project it into 3-dimensional space. So what you're looking at here right now is essentially each dot is just one of the timestamps, and you can see that already there's some structure. So now I can just go ahead and cluster. So I use bottom-up hierarchical clustering to essentially assign a cluster assignment to each time point in this 3D space. Now, this is great, but how do I validate this? How do I know that this works? So the company gave me no data because it's customer data and I'm not allowed to listen to it. So to come up with my own data, what I did is I scraped audiobooks from the internet, free audiobooks, spliced them together, and made just mixed up speaker data. So the algorithm was given this unlabeled data set, but in my back pocket, I always knew who the speakers were because I made it. So using that for this example data set, the points in white are the misclassified points. Across 87 synthetic data sets, I got about 72% accuracy. And so what you heard the demo before was just like one example on just a podcast that I found that would simulate real data, essentially. And so this was my project for Insight. It was a 3-week just project that then we go and we show different companies. DeepGram was really pleased by this. They're like incorporating this now into their pipeline. They're using it in their proof of concept pitches. And if you're interested in transitioning from academia to industry, come talk to me. Thanks.
Thanks, Matar. Seems like a sound venture. All right. So Nathaniel's up next, and then after him is Alexander from HDF Group. Yeah, all right, great. Take it away, Nathaniel.
try that again. I'm going to stay still. Okay. Hi, everyone. At the beginning of the week here at SciPy, I organized a short workshop on Python compilers. I want to give you sort of an update on how that went, what's going on. So why are we interested in Python compilers now? So there's a lot of interest. You know the saying that like if you have a function that takes 12 arguments, then you're missing some? I'm pretty sure I'm missing some Python compilers that people are working on. There's a lot of interest right now. And I was pretty pleased for this workshop. We managed to get a lot of people in the room, either locally or remotely or both, representing a lot of these different projects. And this is particularly interesting for us here at SciPy, I think, that all this stuff is going on because obviously we want our code to go fast. Some of these are sort of numerically oriented projects who, of course, are really target exactly the kind of things we do, but also sort of these like whole language compilers right now are making this transition to trying to get much more compatible with things like C extensions. So in the past, the only thing that could run NumPy is CPython, like the traditional interpreter. But these are already numbers that are a little bit out of date, I think, but these three compilers, Pigeon is now passing the NumPy test suite, Piston is now passing the NumPy test suite, and PyPy is at 96%, maybe even a little more, I'm not sure. And now you might think, oh, that means like PyPy is not as good. Of course, this is because PyPy is by far the most mature of these products, and so they've had sort of more work to do to kind of handle that. But this is really the only production ready, except it's not quite there for now, but we're getting there. Just to show you what 96% means. So here is matplotlib running on PyPy. It's a real thing. Yeah, right? But not all is well. So they can run PyPy, or no, sorry, things like PyPy can run NumPy. But you think about what a JIT does, right? No, it's fine. I'm talking. There's nothing to look at. It can run NumPy, but you think, how does a JIT work, right? It looks at your code and sort of figures out what you're doing and then figures out how to do that quickly, right? Now, what if your code is calling into C? That's just like a black box. It can't look in there. It doesn't know what your code is doing anymore, so it can't optimize it. And we've all spent the last 15 years making sure all the code we want to run fast calls into C as often as possible, right? Oops. So what can we do about this? I think, well, like Numba can take code that uses NumPy and go really fast. And the answer, how does that work? Well, the answer is Numba cheats, right? It sees these, oh, you're calling this NumPy function. Well, I can't go look at that, but I've got here some notes on my own implementation of NumPy that I will swap in place. So talking to them, they say, we're just, 90% of the work we do testing is just check that our implementation of NumPy acts the same as, the real implementation of NumPy. And this isn't unique to Numba. This is sort of the only kind of strategy you can use. So this is kind of what everyone is doing. And this is kind of terrifying, right? This is not a sustainable strategy that everyone implements their own personal, boutique copy of NumPy. There's a number of problems with this. The one that particularly scares me as a NumPy developer is what happens when NumPy changes, in particular because something I'm doing in parallel is trying to figure out how can we make NumPy change a lot more. I cannot make any actual announcements right now, but there are conversations ongoing, and now might be a good time that, if you were interested in coming to Berkeley, working with some really awesome people and also me on making NumPy more awesome, you should come. Let's talk. But so if that happens, it makes a big problem for all these JITs, right? That if NumPy starts changing, you have to keep up, everything's up. Yeah, it's terrible. And it turns out, fortunately, everyone else at the workshop, this was sort of the main thing everyone wanted to talk about. It was the thing that I was worried about. I like it when that happens. And as an outcome of that, we have a cunning plan that sort of everyone kind of agrees is the way forward if we can make it work. So here's, just to give you sort of a rough idea of how this might work. So you have CPython is written in C, but you could have some of it that might be in something like Python. I've got 30 seconds left. Okay. And then if you want to compile this, right, we know this is, you can convert the Python to C, compile it together, run it on CPython. That's all so good, so normal. We know that works. And that doesn't help the JITs. But if you have some of the code written in a somewhat higher level language that encodes some of the logic, you could potentially compile that down to some representation that is not just an opaque binary, but is at a level that is, the Java virtual machine.
And thank you for the eminent vagaries.
And there we go.
All right. Next up is Alexander, and then after Alexander, we will have Matt Rocklin.
So sure, I'm the guy who killed more information about NumPy. So I apologize. I'm Alexander Yannick. I'm from the AGF group. My first time in SciPy, so I thought maybe this is a good way to announce myself to everyone. And tell you something about HDF5. I wrote here HDF5, but somehow I think I wrote 5 as S, so there was a lot of questions about, oh, it's Hadoop distributed file system. I said, no, it's HDF5. So my bad, I apologize. So what's HDF5? It's a library for storing massive amount of numerical multidimensional data. It's used in a lot of places. It's open source. I found quite a few places here that use HDF5 that I didn't know about. And if you're interested about HDF5 and or have some questions, they're already using it, come talk to me. Especially those people who yesterday got the free books, Python and HDF5. You're obliged to talk to me. I think check the signature, probably somewhere in the small print it says to talk to me. I wanted to say 2 things. We released a couple of months ago a new version, 1.10, which is backwards incompatible. So all the versions cannot access the files created with the new version, but 2 features that probably are very interesting to people. One is Swimmer. It's called single writer, multiple reader, which makes more than one process monitor an HDF5 file, and every new data gets notified about every new data and can read the new data as basically immediately after it's written to the file. And there's another one called the virtual dataset, which essentially allows people to access data from external HDF files as they're accessing data from a single dataset in a single file. So it's almost like a little porthole that you can only access data from one dataset and think that the data comes from a single dataset as before, but actually comes from a number of other files. And that's all. We like Python. I use it a lot in our company, and thank you very much.
Thank you, Alexander. And next up, we have Matt Rocklin, who looks surprisingly like Min for some reason. Oh. It's a 3-point circus here.
Yeah.
All right. Oh, and after Min, we'll have Mason, who will be our last talk. Thanks.
All right, so I'm going to talk about something that somebody, Matt Rocklin, who is not me, working on it, said, wouldn't it be cool if you could interact with Dask workers with IPython? So if you haven't, depending on what talks you're in, if you haven't heard about Dask and Dask distributed, it gives you a nice API for doing distributed computing, and so you have a collection of resources that are a bunch of computers that are working together, and I want to distribute my work on that. So I have here, Matt gave me access to a nice little cluster. I don't know where it is, but I know it's not here. And I've connected to that. I have an example, scikit-learn example, classic scikit-learn example from Olivier Grissel, identifying numbers from the common data set. I can step through and do my scikit-learn stuff. Here's my local example, and then do it remote, asynchronous, all the Dask magic, and run these things, and I get nice little widgets. Seeing as that computation happens remotely, this is all the cool stuff that Dask can do. And I can look at the results, kind of get a summary of my partial results so far. But what if something went wrong? So maybe one of my results isn't what I want it to be. And I can Dask lets me say, Dask lets me ask, who has that? Who did that? So I can say, this worker, this remote worker is responsible for this information. Well, I have a pull request open to Dask now that implements a method on the executor called start IPython. And what this does is it starts IPython on that remote worker and then gives me the connection information back for how I need to connect to that. And I have this magic names argument. What did that do? Well, that defined some magics in my notebook. So now when I have a magic, it runs that code on the worker. So I've got worker and worker 2, and then I can run it locally, and you can see that these are on different machines. And then I've put the Dask worker in that remote IPython namespace so I can look at the data on that worker, say, oh, Dask is saving some information about the tasks that this guy's done. Okay, can do some pandas on the worker. I get the nice HTML representation of the pandas table. And since that remote worker is IPython, and I'm talking to it over the Jupyter protocol, I can actually run matplotlib and do some plots. And this plot was actually computed on the worker, which is somewhere I don't really know. And then that information came back to my notebook, which is running on some node on this cluster. But what about from my laptop? So this is a notebook running on my laptop with the nice fancy Jupyter Lab stuff. So you can see the host name, it definitely is my laptop. I can connect to the head node. I can grab a worker. And then instead of passing the magics, I can say Qt console. But since I don't actually have direct access to the worker, but I have direct access to the head node, I can pass extra arguments to SSH tunnel through the head nodes to the worker. And then in a couple seconds, we'll see, maybe. Yeah, I got a Qt console on my laptop connected to a worker that's somewhere. I don't really know. Yeah, that's it.
Thank you, Min. All right, so for the last talk of the day is Mason, and yeah, here we go.
Let's see. All right, my name is Mason Victors. I'm from Recursion Pharmaceuticals, and I'm going to be talking about metric preserving image embeddings today. So at Recursion, we take pictures of cells, of human cells, using fluorescent microscopy. And so these are some examples of these cells under different channels, and here's a nice, pretty composite picture of them to get a sense of the scale of our data. That outline there is of a single cell, and there's about 1,000 of those in a single image, and we typically take 4 to 9 images of a single population, about 300 populations on a plate, and we do between 60 and 90 plates a week, which is about 6 terabytes of images every week that we generate. And it's a really rich data set, and we're trying to use this and our process to be able to find new treatments for rare genetic diseases. To do that, we need to be able to turn these images into a mathematical representation of diseases and drugs and cells. And so we need to be able to embed them into a vector space in a sensible way. We could just flatten them. That would be bad. 5 channels by 256 pixels by 256 pixels becomes a really, really high dimensional representation, just screaming out cursive dimensionality there. Well, we could do some kind of dimensionality reduction on that using PCA, non-negative matrix factorization, multidimensional scaling, take your pick. That has some problems, one being that this is a really nicely labeled data set. We know what these treatments are, and we'd be throwing away that information. The other problem with that is that would be losing a lot of spatial information. So what we can do is use deep learning for image embeddings. So one thing you could do is just autoencoders, which is a completely unsupervised approach to finding a lower dimensional representation of something, but that also loses the label knowledge that we have. You could train a deep convolutional neural network and just take your final layer. That also has some issues. Or you could specifically learn a metric of choice via a Siamese or a triplet network. So we're going to do a demo here, just show some stuff using the hello world of image analysis, MNIST, where you're looking at handwritten digits, single channel. And so we're going to take a look at that right now. So here is a little something I threw together. where we look at just traditional dimensionality reduction initially, using PCA to reduce those images down to 2 dimensions, and we can get a sense of what this looks like, which looks like a really ugly pointillism painting of some kind. Or we could use convolutional neural networks in a Siamese fashion where you feed it pairs of similar examples or pairs of different examples, and you teach it to learn a specific metric. And so we can take look at some examples here. Here we're going to use Euclidean distance here, and we train this model. This one trained it took about a minute last night to do, and you get a really nice 2-dimensional representation here. And some of these different populations are close to each other like you would expect. 4s and 9s are often easily confused. There's an example of a 9 that looks kind of like a 4, and there's a 4 that looks kind of like a 9. And you can see generally in the center of these clusters, you get much better representations. Okay, so that was with Euclidean distance. Let's do a different distance metric. Let's do cosine distance, basically. That actually should be 1 minus that. But you get a pretty star shape, basically, from your data. You're projecting it down, that's sensible. We could use the Canberra distance. I have no good understanding of what this would look like, really, and I have no reason to believe it would be good on images, but let's see what it looks like. And you get some funny representation like this. So the cool thing is you can choose whatever metric you want, and you can actually learn to embed it in a space where that metric preserves the similarity that you define initially based off of your labels to get a really good lower level representation. Obviously, for our stuff, we wouldn't want to put it down into 2 dimensions. That's too low to be able to represent its rich structure, but this is another alternative to standard dimensionality reduction. Thanks.